the stuff we were talking about on Tuesday. So, any questions before we get going?
How's lunch?
How's lunch? Oh, President Worthen's always interesting. Yes. Yeah, good.
Yeah, I kind of had an applications question.
Okay.
And that was when constructing like a fabric based laser,
Mhm.
you have, because one of the homework shows that like the irradiance inside ends up building really high.
Yeah.
What are the most common ways to kind of dump that energy out? Is it just like electrodes on the side to change the?
So it comes down to one of two things. A laser is either continuous wave
Okay.
or pulsed.
Yeah.
And so continuous wave, it's just a steady state thing.
It wouldn't have that high power though.
Oh, it would, yeah. Absolutely. Yeah. That was kind of the point of the problem, is to see how in steady state, how the power buildup goes. That there's a heck of a lot more energy density inside the cavity than what's coming out.
But I guess I have a hard time seeing how that energy keeps its peak in the cavity when.
Well, it's steady state, so the energy going in is the same as energy coming out.
Okay.
It's just that in the transient to build up to the steady state, you have to build up a bunch of power in the cavity in order to maintain the power, the small amount that comes out.
So it's even higher. So okay.
Yeah.
Yeah. Okay. So the buildup is longer than it is.
Yes.
Okay.
Exactly. But speed of light, 1 foot and 1 nanosecond. You've got a foot-long cavity, and even if the buildup is, say, a factor of 100, then roughly 100 nanoseconds, still really fast compared to most phenomena that you're interested in. So the other way to run a laser is as a pulsed laser, and so then you have that buildup, and then you have some mechanism to dump it out real fast. And then build it up again, dump it out. And there, the important things become what's the pulse length and how much energy per pulse, and then what's the pulse repetition rate. And so that's how you characterize a pulse. So if you look at, say, the laser fusion facility at the lab in California. Lawrence Livermore. It's a pulse laser system. And so you have a seed laser, and you split it, and it goes to all these amplifiers, and then there's a whole bunch of chains in the amplifiers, and then you bring it all together, the pulse through each of those amplifier legs, bring it all together on the little deuterium pellet, simultaneously to do the fusion initiation. And then you repeat it. It's a pulse system.
How does a pulse system get in? Oh, I'm sorry.
No, I was just saying that's the mechanism to dump the laser.
Well, how?
So how would you dump it inside the laser? Usually you have a Q-switch laser, and I think we talked about Q-switching, where it's basically beam splitter, quarter wave plate, mirror, polarizing beam splitter, and in there you have an electro-optic cell. And the electro-optic cell, when you have a voltage applied, it looks like a quarter wave plate. When you don't have a voltage applied, it just looks homogeneous. And so you basically switch the polarization state to dump it through the polarizing beam splitter. So that's one way to do it.
So they don't actually do the dumping inside the cavity?
Yeah, that would be inside the cavity.
Oh, so that would be the fabric core. Okay.
Mm-hmm.
Yeah. Okay.
Yep, exactly.
Thank you.
Yep. Yeah, we could do a whole class on lasers. There's so much stuff. Yeah, all the way from the gain medium to the cavity design. Then you have you have stable resonators, unstable resonators, what kind of beams come out of those things, and then how you use those beams, given their properties, the different mode properties of the lasers, transverse modes, longitudinal modes. There's just a whole ton of topics there. And it's fun stuff.
So maybe I'm misunderstanding something, but I think I am. But like, how do you keep the energy from just constantly building inside the
So,
going back to the?
so usually, like in the homework problem, you have a mirror that isn't 100% reflective. So it's
okay.
the transmission through the mirror, that's the outlet. That's where the
Okay.
laser
Okay.
beam is. Yeah. Yep. So that's what limits the buildup. Okay, yeah.
Are you teaching any class next semester?
No, I'm retiring. No, I'm teaching freshman seminar, and I'm doing 360 lab, and then my spring teaching assignment I'm doing next semester, which is 301.
The real one?
Hmm?
The real one?
301.
Oh, yeah, it's like the real one.
The real one, yeah, you know that class, the real one? That's what I'm doing.
I imagine those guys are departments.
Yeah. Yeah, so unfortunately, you know, if you want to regress to 301 level or 360 level, yeah, come see me.
Class 2 or 3 times, or co-taught, I guess,
Yeah,
TA.
yeah.
Oh, yeah.
Yeah, Jason?
Do you happen to know if they're going to be offering any grad classes in spring at all?
Usually there aren't, unless it's in an area I'm not familiar with. So, yeah, but it's usually rare. There might be a signal processing class or something, but I don't know. Yeah.
Do you teach any other grad classes?
Nope. The writing class sometimes, which is actually, I love teaching that. That's great fun. Because I make you guys do all the work. No, we learned some really good things there. It's good. No, this is really the only grad class. Just it's kind of how it evolved with things when I came here. So yeah, but we did a lot of research. So you definitely get an education doing that, right, Matthew and Mona?
Yep.
Yeah. Yeah, that's fun stuff on Clayton. Yeah. Okay, any other questions? All right, so you're ready for the finale then, in terms of what all this absorption dispersion stuff is leading to? Okay, so we talked last time about how if you have a refractive index that is wavelength dependent, then necessarily the absorption is also wavelength dependent, and they fulfill a very particular relationship, namely the Kramers-Kronig relationship, the Kramers-Kronig equations. So we wrote down the Kramers-Kronig equations in terms of the electric susceptibility, real and imaginary parts. And then we said, usually, you're not going to measure the real part of the electric susceptibility with the imaginary part. Instead, that's normally what you measure. And so you can transform the Kramers-Kronig equations so that they're in terms of refractive index and absorption. Since that's what you tend to measure, it makes it easy to calculate that based upon an absorption measurement. And so what we found is that the real part of the refractive index as a function of photon energy, so photon energy is h nu or hc over lambda, whatever, is equal to 1 plus hc over 2 pi squared, integral 0 to infinity of the absorption coefficient as a function of photon energy divided by photon energy squared minus photon energy squared. So the prime is the integration variable. And so basically that's just saying that, hey, if we measure the absorption coefficient, we can calculate this integral and get the refractive index. So that's a very handy thing to be able to do. And what we want to do now is take a look at just kind of generally how this works. And so I'm going to do this in a couple of stages. Yeah.
Really great. That alpha in the integral is alpha multiplied by e prime, not alpha as a function?
It's a function of the photon energy.
Okay.
Yeah. Okay, so let's do the following. Let's let's say that we have the absorption coefficient as a function of frequency, and we measure some absorption at a frequency nu naught, and then it's going to look, something like this. Generally, you have some absorption peak, and it has some spectral width centered on nu naught. So if I had this sort of absorption, it's kind of Gaussian, Lorentzian, whatever you want to call the line shape, and I took that absorption coefficient, I plugged it in here, and I did this integration, the question is, what would it look like? Meaning, here, for the real part of the refractive index, what would the shape be? And if we draw in 1 here, meaning that piece of it, it turns out that it would look like this. You'd do something like this. Okay, where this, is the spectral width, and then you notice here in this region, what's happening? We have, as the frequency decreases, the refractive index decreases. If frequency is decreasing, the wavelength is what? Increasing. So we're going longer wavelength, we're getting smaller refractive index. We saw that on Tuesday. That is normal dispersion. But notice as we get out over here, it goes flat. And in fact, it asymptotes above 1. And that is a key point. Because what it means is that the absorption at nu naught affects the refractive index at all frequencies smaller than nu naught.
Can you say that again real quick?
The absorption at nu naught affects the refractive index at all frequencies less than nu naught. But not at frequencies greater than nu naught. I mean, this just asymptotes to 1.
Interesting.
Yes.
That's really weird.
It's pretty wild. And this is a crucial phenomenon.
So how do you observe this? Do you just plot this equation for different values? Or like, how do you? I guess how did somebody notice this?
That's a long story.
Okay, never mind.
Yeah. But the summarized version of the long story is this relationship, which you can visualize for the case of a simple single absorption here.
Okay.
So real materials, though, have more than one absorption band. Yeah, Wes?
Real quick, what happens in the middle there where the index crosses?
Here?
Is that 0? Why is it crossing 1?
Yeah, it's crossing 1, and then here you notice it gets less than 1.
Yeah, what's going on there?
Yeah, well, so it's just saying something about the phase velocity. But notice all of this action is happening in the middle of your absorption. And so over here, notice that the dispersion is the opposite is over here. So this would be a region of anomalous dispersion. And just looking at this simple case, you realize, oh, anytime I have anomalous dispersion, I'm right smack dab in the middle of absorption. So I'm not going to get much light through. So you'll often see people who are playing up anomalous dispersion as a way of doing whatever, some cool thing. But whenever you hear that, at least in my mind, I always say, yeah, okay, but it just means you got a lot of absorption, so prove to me that the loss isn't gonna kill you. So, yeah, and you remember we saw that the real part of the refractive index for metals tended to be less than 1,
Right.
because we're in this region. Okay, so let's try a situation where with our absorption coefficient, we have more than one absorption resonance. So let's say that we have something over here in the UV, say something that looks like this, and then let's say over here we have something in the infrared, and let's say it does this, and then over here we've got something in centimeter wave region, and the absorption does something like that. And so what we want to do is look at what is the real part of the refractive index, and let's draw in the value of 1 here. And then let's call this, say, mu1, mu2, and mu3. And we know from over here that any absorption resonance is going to affect the real part of the refractive index for all lower frequencies. So that means we better start on the high frequency side to see what's going to happen here. And so I'll just draw it in a different color so I have a little more contrast. So basically what we'll see is something that looks like this. And you notice this is kind of broad because that's kind of broad. And then we have this offset. So it's just like this. And then this thing's really sharp. So this comes along and does something like that. And so we have more of an offset here from the second absorption resonance. And then we come to this guy, and we have basically these offsets have built on one another.
Do they just add together?
They just add. And so we've got quite a bit more offset. Because the absorption resonances, their smaller frequency tails all add on top of each other. Yeah, exactly. Which is kind of wild.
So is this top one saying this is like some material that has absorption at these?
So, many materials will have an absorption resonance in the UV, in the infrared, in the centimeter wave region. What are these things due to? Well, usually this is due to atomic transitions, electron transitions within the atoms themselves. So different, going between different energy levels in the atomic shell structure. And then these tend to be from things like molecular resonances. So you have different vibration modes in molecules. So that will tend to be this. And then this will tend to be things like phonon resonances. So you have a solid material, and you can get vibrational modes in the solid material. And so that could be where this absorption is coming from, is coupling into those vibrational modes. And so, that would be just kind of typical for some material.
And so what we're doing with this top graph pretty much is grabbing this graph and plugging it into this NOP.
Yep.
And this
We're
is
doing
the
the
graph
generation, and this is what we get for the real part of the refractive index.
For the real part of the refractive.
Yeah, and if we want the imaginary part, well, that's no big deal because alpha is directly proportional to the imaginary part of the
We just use
refractive
like
index.
4 pi.
4 pi over lambda times the imaginary part of the refractive index, so it's easy to get.
You call these absorption tails? No.
Which, here?
Yeah, that all add up.
No, this is absorption.
That's absorption, those are the dispersion.
So these are the, yeah, just the, sort of the DC offset in the real part of the refractive index created by a higher frequency absorption resonance. So as I've drawn it then, this would be the visible. And notice in the visible how it looks. At shorter wavelength, meaning higher frequency, higher refractive index. Longer wavelength, meaning lower frequency, lower refractive index. That's normal dispersion. So remember we looked at the glass refractive index as a function of wavelength, and it always decreased as the wavelength increased. So that's why. That's what's going on. And anytime we get into a region where the refractive index is dipping below 1, well, we're in the middle of an absorption. Or if we have anomalous dispersion here, we're in the middle of an absorption band.
What does it mean for it to click below the 1?
We're not too worried about it. Yeah, for our purposes and the time we've got, no, we're not going to worry about it.
But it's a
Would
metal.
that like conceptually mean it's moving faster than light or
No,
something?
it's not. I mean, so you have the, what is it, the phase velocity and the group velocity.
Oh, okay.
So the phase velocity, yeah, okay, faster than the speed of light, but information travels at the group velocity.
Okay.
So in practice, no, there's no violation. Yeah. So, okay, so do you remember how we said way back when that the permittivity of a dielectric medium, we can write it as permittivity of free space times dielectric constant. And we said that refractive index is the square root of the dielectric constant. Remember that? So you may also remember, or maybe you don't, that I said that I've seen numerous times students wanting to know the refractive index of glass. And what they do is they go look up what's the dielectric constant of glass, and then they take the square root and they say, oh, I got the refractive index. And they get a value like 8, 9, 10. It's because the dielectric constant they looked up is the DC dielectric constant. They're getting this, but it has nothing to do with the refractive index in the visible portion of the spectrum. And so, this dielectric constant, you typically see that for, if you're doing electronics, then you're getting the value that's good at DC, a megahertz, a gigahertz, all very low frequency stuff compared to optical frequencies. So that means you're below these absorption resonances, so you're picking up the effect of those resonances. So that's why you have to be really careful to make sure when you're looking for physical constants to pick them out in the right frequency range.
So some of these tails can be pretty dramatic. Right?
Oh, absolutely, yeah.
So why would they give you, if you look it up online, why would they give you the ER for way down there?
Because that's what's usually available because people are interested in what's going on for electronics. To design a transmission line or something.
Okay.
Yeah. And that's all just really super low frequency stuff compared to optics. Yeah.
So I guess on like a physical level, so does every material have the same kind of peaks?
They have some kind of
They have some kind of peak, and is that just, like, what causes that? Is that just, like, energy being able to be coupled in because of, like, electron levels, or, like?
Yes, well, so it's different depending upon the thing, but this would be electron levels,
Okay.
and this would be molecular vibrational modes,
Okay,
and these are phonon modes
okay,
of the crystal or solid material.
okay, makes sense.
By the way, Dr. Mazzeo, 662, our class, that he taught this semester, really has discussed that quite well, so if you're here in 2 years,
Yep.
Hopefully I'm not still taking classes in 2 years.
they'll cover that.
Yeah, which is fascinating stuff. It's good stuff.
It's quantum mechanics, basically.
Yeah.
That's right.
So, what are the ranges again for normal and abnormal dispersion? I mean, obviously normal's on the left, but like, does it start at the peak of that hump, or is it more a level area?
So normal dispersion means that the refractive index is going up as the frequency is going up.
So from that peak downwards.
Yeah, so if I'm here and I go this way, refractive index is going up, frequency is going up. Which is the same thing as saying, as the wavelength is going up.
So on the other side there, that's also the case to the bottom peak, is that?
Here, yeah.
And that's also considered part of normal dispersion.
That would be normal dispersion.
So the place in the middle is the one that's not.
Anomalous dispersion. And anomalous dispersion is always in the middle of the absorption peak. So, let's say you're making a Fabry-Perot, and for whatever reason you need anomalous dispersion to make your modulator work. Well, forget it, because you're going to have a bunch of absorption in there. Your Fabry-Perot is not going to work well.
So what are some use, so it looks to me like this is a neat property that could have some uses, the anomalous dispersion property.
Yeah, it is, but there's always the absorption problem. So you always have a lot of loss. So, over the years and decades, really, I've seen numerous people put forth these little, interesting ideas that create mini bads. But, when they're based on this thing, it's always the same problem. There's too much absorption, so forget it. Why even go down that path? So if you can figure out if your application is absorption tolerant, okay, fine. You might have something, but you just can't get rid of the absorption and only deal with the anomalous dispersion. Okay, so now you know how it works. So I suppose what we could do is draw a graph that shows things as a function of wavelength instead of frequency. So it basically takes that and flips it. So we might have absorption, that looks something like this over in the UV. And maybe we've got something that looks like this in the infrared. And so the real part of the refractive index is a function of wavelength, might look something like this, somewhere in there. And so here we've got the visible, and you see we've got a region of normal dispersion, and pretty much no absorption. And so that would be something kind of typical that you could measure. Now I should point out a couple of problems. One, you're trying to do this calculation. Let's say you take the spectrometer available in our lab. You can make a measurement from over here, 190 nanometers, out to, Matthew, do you remember? On the long wavelength side, how far out it goes?
For what?
For a spectrometer?
I don't.
Okay, I think it's 2 microns. So it might be 1950. nanometers.
Because we're at like 450. Yeah, that sounds about right. Because we're like at a quarter of the way.
Yeah. So, so if you can make this measurement of absorption great, then you can do this integral from 190 nanometers to 2 microns. And so in here, you can probably do pretty good in terms of the refractive index. But out here or out here, nah. You're not going to be able to use this to get it. In other words, extrapolating doesn't really work well. You need the measurements for the absorption. Okay, so any questions? We're good with how it works? Okay, I can show you an example of where we used this some years ago. So we had a situation where we had a substrate, silicon, and we were doing some photoresist on there. And we had 2 beams instant from the same laser source. So these are roughly plane waves. So what's going to happen? Interference. So we're looking for an interference pattern that did this. And then that would expose our photoresist. And then after we develop the photoresist, basically we have something that looks like this. So, easy way to make a grating in photoresist, and then we could etch the silicon. Okay? Rather than using a mask in the mask aligner, we did this because, and you might remember the papers I showed you, we wanted this to be a 1 micron period. And if you wanted say a 50-50 sort of split between photoresist and no photoresist, then you would need a 500 nanometer line here and a 500 nanometer space here on your mask. Have any of you made masks for the clean room? Can you get 500 nanometer lines? Nope. Nope, not with our Heidelberg system. If you want to pay a lot of money to a mask house, can you?
Probably.
Yeah, you can.
Can buy anything.
Because I've done it. In fact, I did it in the 90s. And I can't remember how much we paid for a mask, $5,000. You know, for one mask that had 1 centimeter square here with 500 nanometer lines and spaces. And then you try to take that into a mask aligner, contact mask aligner, and do the pattern transfer. How well do you think that works? That's tough. And the only way it works is if you get really good contact between the mask and the photoresist. The only way to get good contact, or good enough contact, is using a vacuum contact mode. It's the only way to do it. And if your aligner does not have a vacuum contact mode, forget it, it's not happening. So the poor man's way of getting these kind of features is just do interference lithography. Yeah, Jason?
So, but doesn't that produce a circular pattern?
It'll be the whatever the beam shape is, yes.
Okay.
That's right.
So, you said that those are 1 micron?
Period.
Period?
Yeah.
So where's the 500?
Well, if you want a 50-50 duty cycle, so 500 nanometer line, 500 nanometer space.
Wow, how small can you get with that?
Interference lithography? Oh, you can get really small. I mean, it's just a matter of, if you go back to the last homework assignment problem, whatever it is, 6, 7, 8, just increase the angle. And then that makes the period smaller.
Okay.
So if you wanted a 200 nanometer period,
Just use it as-
yeah, you can do it, it's not a big deal.
So they're just like immersion lithography, you know? What that is,
Immersion lithography is you have an imaging system where you have a mask and you're demagnifying it into, so the image, demagnified image at the photoresist plane. And the material between the final lens and the photoresist is not air, it's a liquid. And because it's a higher refractive index than air, you can get a higher numerical aperture, and then your resolution is dependent upon the numerical aperture. Higher the numerical aperture, the better the resolution. So at any rate, it turns out that when we did this, we were left with photoresist that looked like this. And then, so why?
Is there no interference mode in there?
Yes.
The longitudinal one?
Well, how? I mean, what else is interfering here? Last time we calculated the reflection from silicon, what was it? Yeah, 38% or something for the example we did. So you basically have these two beams coming in, and then you have a significant fraction of them reflecting back out. And so, this one interfering with its reflection gives you an interference pattern with fringes this way. And that's what's causing these guys. And for us, the real kicker was down here. We have a null in our interference pattern, so we always end up with photoresist down here. And that was really a problem because we needed to etch the silicon.
Yeah.
And if you got photoresist there, then it's not happening. So, as a solution, I found this material that was called an anti-reflection something or other. BARC was the trade name, B-A-R-C. And the AR was anti-reflection. And basically what you do is you put down the, let's just call it an arc layer. And then you put down the photoresist. And now what happens is, bring your two beams in, you get interference here, and then the purpose of the arc layer was to absorb the light that's instant so you don't get any reflection from the silicon. And then what would happen is, after you develop is you get this in your photoresist, and now you've got to transfer the pattern through the arc and then do through the silicon. Okay, so we needed to know the absorption spectrum of the arc, and we needed to know its refractive index. So this is what we did. I guess we need this. Okay, there we go. Okay, so over here, K, that's the imaginary part of the refractive index, which is absorption. And this is wavelength. And so here is our measured absorption spectrum. So it's not just a peak, it's something more complicated. But it doesn't matter, you can still do this. It's just a numerical integration. And this is the refractive index that we calculate because of that peak, or rather that absorption. And we needed to do that because we had some stuff that some optical things we wanted to figure out in the arc. But at any rate, this worked great. It's borne out in practice. It's not just theory.
Did you have to have some sort of starting value to calculate?
This was done so long ago, 20-some odd years ago, I don't remember that.
Because it seems like if you, this narrow band, you need to know kind of more details further up.
Yeah, I don't recall. Yeah, could be. It's just been a long time. Okay. All right, well, that concludes it for our discussion. So now we need to get to the logistical stuff.
Quick question real quick. So
Yeah.
don't you wind up with the same problem of the arc layer blocking the silicon?
Yeah, but it's easy to etch through it because it's an organic layer, so an oxygen-based etch. And then the key is you want it to be directional. So that means you want this to be thin, and then you're playing a trade-off game between directional oxygen etch, which doesn't exist, and enough absorption that you don't get this problem. Yeah, but we were able to play the game. It worked out fine. Okay, so I guess we need homework 7 turned in, right? So tell you what, just keep it.
I'll just give you credit for it.
And here are solutions for homework 7, solutions for homework 6, and a final exam. And here's homework 6 if you want to pick it up. So come on up. Yeah, that's the one thing I forgot to print out.
We can wait.
Yeah. Yeah.
Early Christmas present?
Yeah.
I have due Tuesday by 5 p.m. handed into the
Yeah,
office.
Tuesday by 5 p.m. handed into the office.
Tuesday by 5
And remember, what is it open and what is it closed?
People.
Closed people,
Open notes, homework and stuff.
open notes, homework, vote. Fine with it? Yeah. I recommend not leaving here without it.
Oh, yeah. 40% of your grade right there if you lose it.
Yeah.
So in SEM, it was fun. So we have a written part of our final. We took SEM a hands-on one. We have to do this next week.
Uh-huh.
The last question on the written one is how much do you want each one to be worth? Like, because it's 30% total. He's like, but you can shift it however you want.
Wow.
And I was just like, oh man.
That's nice.
I mean, it's nice, but at the same time, it's like, oh, I know I did well on the written,
Yeah, you
but like, am I gonna do better on the hands? Like, I don't know. It just like messes
you have
with
to
you.
be, you have to know what you
Yeah,
know.
I took the second one.
Yeah.
I would weight
Yeah.
mine totally wrong because I'm always worst scorer on the most confident answers.
Well, see, that's the thing. Is like I felt really good about the written stuff because I studied a lot, and then I did really well on the hands-on one before.